Hi everyone, welcome to this video on vector calculus. Today we'll be going over 4 different questions on vector calculus, starting from the pure math, working towards calculating voltages and currents and powers in complex domain. So let's dive into the question number 1. The first question is saying find the polar form of the complex number -4 plus j3. So essentially, what I would suggest first is let's plot where this complex number resides on the complex axis. So imagine that this is the real and imaginary axis of a complex domain. If I want to locate -4 plus j3, it would be sitting somewhere in the second quadrant. Let's call it A. It's always important actually for us to recognize which quadrant actually this number is sitting. In terms of the polar coordinate, we need to find the length of this line that connects A to the center and call it the magnitude of this number. And so let me just draw that. So this would be called the magnitude of this number, and also the angle between that line and also the real axis is called the theta. So I would call it magnitude of A, and phase as theta is going to be representing. So essentially, this A is represented with an amplitude with a phase, or also an amplitude and phase representation as we can show with an angle. And it is important to recognize that how the amplitude A is going to be computed. It is essentially the square root of the the real part, which in this case is -4 squared, plus the imaginary part, which is 3 squared. It's essentially the Pythagoras theorem that calculates this edge of the triangle that is calculated with these edge sides of 3 and 4. So essentially this becomes simply 5 as the magnitude. However, in the phase, typically what we calculate is the arctan of the imaginary of a number divided by the real part of the number. But then we need to be mindful of the fact that when there is a negative component in terms of the real or imaginary part of that complex number, we need to take care of that into our consideration when we are calculating this arctan through a calculator, because the calculator would always give you a number that might not be determining whether the point that we are referring to is in the second quadrant, for instance, in this case, or in the fourth quadrant, because in both cases, or like for this case, it would be either -4 and the as the real part and 3 as the imaginary part, or 4 as the real part and -3 as the imaginary part. So in that case, we could also call this point to be A prime. Our calculator couldn't recognize the difference between these points, because essentially in calculation of the imaginary part divided by real, we would still get the same value. So the calculator would always result in a number that is between -pi/2 and pi/2. So this number would be from -pi/2 and less than pi/2 in radians. However, if our location is not going to be in neither of the first or fourth quadrant, we need to add 180 degrees to that in order to compensate for that. So, however, there is also a simpler way to do that. So I would recommend to, first of all, calculate this triangle and create this triangle on this complex plane, and then try to find this little angle that is less than 90 degrees, and that is doable with a calculator. However, this theta prime, if I want to call it this way, theta prime is going to be complementing the original theta that we have. So when we calculate the angle theta prime, we need to subtract that from 180 degrees to get to the value of theta. And the reason for going for theta prime rather than theta is that theta is larger than 90 degrees and calculator doesn't give the correct answer. However, theta prime is less than 90 degrees and we can use the calculator to that. However, with respect to theta prime, we need to consider that now we are dealing with this triangle and the arctan of this is no longer going to consider the negative values. It will always be positive values because the front length is going to be 3 and the side length is going to be 4 in magnitude. And in that case, let's try to find the the angle of theta prime, which is going to be arc tan of, in this case, 3 over 4. And remember that we are using the absolute values here. And if you're using this, so the calculator would give us the number of 36 degrees, roughly 36.8. Now, theta in this case is going to be 180 degrees minus theta prime, which is going to be around 143.2 degrees. So essentially, this is the correct angle of our question. So finally, A can be written as magnitude of A, which is 5, with an angle of 143.2 degrees, which, as you can see, is sitting in the second quadrant. So that's how we would calculate the polar form of a complex number. So let's dive into the second question. The second question is saying calculate the impedance of a circuit where a load with a 30 with 20 degrees ohms is in series with a parallel combination of an inductor with impedance of blah 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 and a capacitor with this impedance. Express the total impedance in polar form. So let's make an equivalent circuit diagram. Since it's saying that there is a load that is in series with parallel combination of an inductor and a capacitor, so we're dealing with something like this. So there is a load that is in series with a parallel combination of an inductor and a capacitor. So I would call it Z1, and the inductor can be Z2 and the capacitor can be Z3. Now we know the values of Z1 and Z2 and Z3 indeed. So Z1 is given with 30 with 20 degrees. Z2 is an inductor and is given with 25 with 45 degrees, and Z3 is given with 15 with an angle of minus 60 degrees. So essentially, when we are going to actually find the equivalent Z, when we're looking from the outside, or Z equivalent from these 2 points of A and B, essentially Z equals Z1 plus parallel combination of Z2 and Z3. And if you want to simplify that, it essentially is Z1 plus 1 over Z2 plus 1 over Z3. Now, we have all of the values of Z1, Z2, and Z3, so we can actually simply replace over there. So Z equals Z1, which is 30 degrees with 20 degrees plus 1 over 25 with an angle of 45 plus 1 over 15 with an angle of minus 60 degrees. Now that we are going to actually simplify this denominator, it seems to be not quite easy to do that in polar form. So it would be better to convert them all into rectangular forms so that our calculation would be easy. Similarly, for this one, we can convert them all in rectangular form because summation and subtraction is easy in rectangular form. And in order to do that, we know that for each one of Z1, which is 30 degrees and 20 angle, it can be represented as 30 cos 20 degrees plus 30 sine 20 degrees in terms of in times j to convert that into a rectangular form. So essentially cos of this angle times the magnitude gives the real part, and sine of that angle times the magnitude gives the imaginary part. So if you simplify this um, for all of the Z1, Z2, and ZL and ZC, I'd like to just simplify this for ZL. In this case, it's going to be 17.6 plus J 17.6, and ZC would be 7.5 minus J 12.99. So we can see that using these two, we can simplify the denominator, as we in the denominator we have 1 over ZL plus 1 over ZC. So if you simplify 1 over ZL plus 1 over ZC using the calculator, you would get to the value of 0.062 plus J 0.029. So that will be what is the denominator over here is saying. So that's 1 over Z, the parallel. So in that case, when we are reversing that to get the Z parallel, we will have simply Z equals 30 degrees with an angle of 20 plus 1 over 0.062 plus J 0.029. This becomes simply 10 ohms with an angle of minus 25 degrees, and this stays as 30 ohm with an angle of 20 degrees. So if you simplify them again, it's easier actually to sum up these numbers in rectangular format. So 30 again cos 20 plus J 30 sine 20 degrees plus 10 cos minus 25 degrees plus J sine minus 25 degrees. So if you simplify that using calculator, you will get to a number that in the polar format, it would be 44 with an angle of minus 25 degrees. So this Z equal has a magnitude of 44 and a degree of minus 25 degrees. So essentially, if you want to actually convert a number that is in a plus jb format to a polar form, the polar form of that has a magnitude of a squared plus b squared with an angle of tan inverse of b over a. And we need to be mindful of the fact that if this is sitting in the second or fourth quadrant, we need to consider these small angles with respect to that and use the complement angles in order to get the correct phase. So let's move on to the third question. So now let's dive into the third question. The question is saying a load operating on a single phase AC circuit has a known apparent power of 150 volt ampere and a power factor of 0.75 lagging. If the voltage supplied to the load is 120 volts, determine the current drawn by the load and the active power it consumes. So we know that the way that the apparent power is related to the voltage and the current is S equals V times I conjugate. So we call S to be the apparent power. That is a multiplication of V in complex number and times I, which is also a complex number, which essentially is a complex number in general. And we can break it down into P plus JQ. And in this case, P is the real power or active power, and Q is the reactive power or imaginary. And also we have the power triangle that is related to R, X, and Z as follows. So we can have R I squared, X magnitude of I squared, and Z magnitude of I squared. We can call them as P and Q and S in simple terms. So essentially, when we are talking about the angle or theta, this shows that S times cos theta is P. And in this case, cos theta is the power factor. Cos theta is essentially P divided by S. So these are the information that we will be using to solve this question. When the question is saying that the apparent power, or S, equals 150, and also it has a power factor of 0.75. So it means cos theta is 0.75. So using this equation, we know cos theta and we know S, so we can easily find P. So P is essentially S times cos theta. So 150 times 0.75 is going to be simplified into 112.5 watts. This is the active power that we were asked by the question, active power that it consumes. There's also other part of the question that says find the current drawn by this circuit. So we know that S, or the apparent power, is 150, and also it's a multiplication of voltage times current. Now we know the voltage as well because that's 120. Then S equals VI, and in this case 150 times I equals S, which is, well, 120, I is 150, and then I then becomes 150 divided by 120, which is about 1.25 amps. So here is our current that is drawn through the circuit. So let's dive into the fourth question. Calculate the line currents and total apparent power for a three-phase system with parallel loads having impedances of 4 plus J3, 6 minus J2, and 5 plus J4 ohms, respectively, supplied by a 415-volt source. Include the phasor diagram for source and load and voltages and currents. So let's dive into the fourth question. The question is saying calculate the line currents and total apparent power of a three-phase system with parallel loads having impedances of 4 plus J3, 6 minus J2, and 5 plus J4 ohms, respectively, supplied by a 415 volts source. So let's just draw a circuit diagram of this three-phase system that has parallel loads. So essentially, we have three parallel loads that are supplied by the same power source of 415 volts, and we know the impedances of each one of them, like Z1, Z2, and Z3 are as follows. So Z1 is 4 plus J3, Z2 is 6 minus J2, and Z3 is 5 plus J4. In order to find the parent power, we know that S equals V times I conjugate. We know the voltage across each one of those Z1, Z2, and Z3. The only thing that is remaining is finding the current that is passing through them. So in order to find that, we need to divide the voltage across them by the corresponding impedances. So essentially, if I'm going to have a current of I1 over IZ1 and I2 over Z2 and I3 over Z3, but those values of I1 would be equal to V divided by Z1 essentially. So 415 volts divided by 4 plus J3. And if you calculate this and simplify it, you would get to a value of 66.4 minus J49.8 amps. Similarly, I2 becomes voltage divided by Z2, and in this case, 415 divided by Z2, which is 6 minus J2. And if you calculate that, it will be 62.25 minus plus J20.75 amps. I3 is going to be V divided by Z3 and equals 415 divided by 5 plus J4, and the result is 50.61 plus or minus J40.49 amps. And in order to find the parent power, we need to just multiply. So S1 would be V times I1 conjugate. In order to find a conjugate of a component, we just needed to make the sign of the imaginary part multiplied by a -1, which in our case, it would be the voltage is still 415 times I1 conjugate would be 66.4, and in this case, plus J49.8. Remember, this plus is versus this negative, that's how you make the I1 conjugate with respect to I over here. So essentially, this is S1, and if you multiply that, you would get 27,556 plus 2667 J volt amp. Similarly, S2 becomes V times I2 conjugate, and it will be simply 415 times 62.25, this time minus J20 times 75. Remember, again, this is the current, and this is the conjugate of that current, and in order to do that, we negate the imaginary part. This simplifies to 25,833 minus 8611G. And in this case, I'm going to write the final answer as 21,003 plus J16802 var. So these are the apparent three-phase powers, and the total S total is simply S1 plus S2 plus S3. So essentially, we have three complex numbers, as you can see here, S1, S2, and S3, and they are all in rectangular form, and they can be easily summed up with each other, and that's how you would get to the total S of this circuit. The total apparent value would be equal to 74,392 plus J28858. I'm just writing them now in order to double check with your answers as well. So this is how the the apparent power of each one of those components can be calculated. And here is the fifth question. that I'm leaving as an assignment or a practice for yourself to solve. And if you can find any, and here is the fifth and final question that I'm not going to be solving it, but I'll leave it as an exercise for you guys. Please make an attempt, and if there is any issue or question regarding this, please leave your comment below the video. And also hit like and subscribe if you like this type of videos more in the future. Have a great day.